So this is homework number 10, question number 5, and the question is stating x or 2x squared y double prime plus xy prime minus y is equal to x when x is greater than 0 and when y1 of x is equal to x. So we're gonna need to use the reduction method to solve for this equation. To do that, we need to state that our y2 of x is going to be our v times y1. And since we know our y1 given in the equation, we can say that is going to be v times x. Therefore, our y2 prime is going to be equal to v prime of x plus v. And our y2 double prime is going to be equal to v double prime of x plus 2v prime. Therefore, we can state, or we can replug this back into our original equation, which is up here, and state that 2x squared times v double prime x plus 2v prime plus x times v prime of x plus v minus vx is equal to 0. So simplifying this out, we get the equation 2x cubed v double prime plus 5x squared v prime, which is equal to 0. And now we can't really solve this equation. So in order to solve this equation, we have to state that z is going to equal v prime. And therefore, since z equals to v prime, z prime is going to equal to v double prime. Okay, now that that's all set up, we can plug this back into our original equation, or not our original equation, the new equation, and state that 2x z prime plus 5x squared, this is 2x cubed z prime plus 5x squared times z is equal to 0. Now we can do variable separable with this. Simplifying it out, we are going to get z prime over z is equal to negative 5 over 2x. Now we need to integrate it to get it where it needs to be. In doing that, we get the integral of z prime over z times dx, which can be rewritten due to chain rule and other such rules. We're going to get the integral of 1 over z times dz, which is equal to, say, our integral negative 5 over 2x dx. Therefore, the integral is going to be ln of z is equal to negative 5 halves ln of x. Therefore, we can say that z is equal to x to the negative 5 halves, which is also equal to our v prime. Continuing on to the next page, rewriting that up at the top, we got z is equal to x to the negative 5 halves, which is equal to v prime. Now that we have solved for our z and v prime, to get rid of the prime, to find v, we have to take the integral of z, which is the integral of x to the negative 5 halves dx. In doing so, we are going to find that v is equal to negative 2/3 x to the negative 1/2. Therefore, our y of c is equal to c1 of x times x plus c2 x to the negative 1/2. Now, we need to find our yp. So we are going to state that our yp is some function of x times x. Therefore, we can say that our y prime of p is going to equal to w prime times x plus w. And our y double prime of p is equal to w double prime of times x plus 2w prime. Now we're going to use the reduction method again and to find that our z is equal to w prime. Therefore, our z prime is equal to w double prime. Rewriting our equations, that is going to give us we don't do that step yet. We have to rewrite it back into our differential equations, our original differential equation, which is going to be 2x squared w double prime times x plus 2w prime plus x times w prime of x plus w minus wx, which is equal to x. Simplifying out the equation, we're going to find that 2x cubed w double prime plus 5x squared w prime is equal to x. Now we take our z is equal to w prime, which our z prime is equal to w double prime. Plugging this back into our equation, we're going to find the equation our equation ends up being z double prime times 2x cubed plus z times 5x squared, which is equal to x. Now we need to get z double prime by itself. Excuse me, this is just z prime. Z prime by itself. So to do that, we're just going to divide everything by 2x cubed, giving us z prime plus 5 over 2x times z, which is equal to 1 over 2x squared. It's supposed to be 2x cubed there. And now we can use our integrating factor method to solve for this one. And to do that, we're going to start on a fresh sheet of paper. Writing it out, we're going to find that our z prime plus 5 over 2x cubed times z is equal to 1 over 2x cubed, or squared, sorry. So, in doing this, using our integrating factor method, we're going to find that our p of x is equal to 5 over 2x cubed. Therefore, our integrating factor is going to be equal to e to the integral of p of x dx, which is equal to x to the 5/2. And our q of x is going to be equal to 1 over 2x squared. Plugging it into the equation, z times our integrating factor, which is equal to the integral of the integrating factor times q of x dx. We can plug in our values, giving us z times x to the 5/2, which is equal to the integral of x to the 5 halves times 1 over 2x squared dx. Writing this out, we're going to find out that this will be equal to integral of x to the 5 halves power over 2x squared dx. Rewriting it, you can see that it will become x to the 1/2 power over 2 dx. Integrating it at that point, we can say that it will be x to the 3 halves over 3, which is equal to our x to the 5 halves times z. Dividing the 5 halves over, we get that our z is equal to 1 over 3x, which is our w prime. Therefore, our w has to be equal to the integral of z, which is equal to the integral of 1 over 3x dx, which is equal to 1/3 natural log of x. Therefore, we can say that our y of p is equal to x to the 3rd natural log of x. Therefore, we can say our general solution is equal to y is equal to y of c plus y of p. And then with that, we can say that c1 x plus c2 x to the negative 1/2 plus x halves times natural log of x is our general equation, and that is the solution for this problem.